Hello, in this video I want to work through an exercise on models to help us get to understand more how models work. So this document is the models exercise. This says with solutions, but the one that's posted right now is just the models exercise. So what I'd like you to, and it should be just below this video in the window you're watching this in, and I'd like you to print that out and then work through these exercises with me. And there's also a models homework document also down there, and that's part of the homework that you have for Thursday, and you need to submit that through the Canvas site through the assignment that's also linked in this window, or below this video window. So the first sort of things we're going to do is we're given a model and we're asked to determine the truth value of various sentences in that model. So here we have a model whose universe is 0 and 1, and that means that there are two things that we're talking about that our quantifiers concern, and they don't concern anything else. And the two things are the number 0 and the number 1. Then we have the extensions of the three predicates. And by the way, this 1 in brackets, just ignore that. Don't worry about that. Forget it. It doesn't matter right now. Don't worry about it. This over here is the extension. So this tells us that f is true of 0 and it's false of 1. It's false of everything not on this list. This tells us that g is true of 1 and false of everything else, so false of 0. And h is the same. It's true of 1 but not true of 0, and so it's false of 0. So we have this universe, two objects. We have one property, or one predicate, f, that's true of 0, and one predicate, two predicates, g and h, that are true of 1. So let's look now at some sentences. So we'll start with for all x, if fx, then hx. So when is this true? Well, it's true when for each object in the domain, when we assign it to x, then this comes out true. Okay. So what happens when we assign, so it needs to be the case that when we assign 0 to x, this is true, and when we assign 1 to x, that's also true. So if we assign 1 to x, then let's see, is hx true or false? Well, 1 is in the extension of h, so h is true of 1. So when x refers to 1, hx is true. So that means that when we assign 1 to x, hx is true, and therefore the whole conditional is true, because a conditional with a true consequent is true. So when we assign x to 1, the conditional is true. But what about when we assign 0 to 1? Well, when we assign 0 to 1, then fx, f is true of 0, so fx comes out true. What about h? Well, h is true of 1, but it's false of 0. And so when x refers to 0, hx is false. So when x refers to 0, fx is true, and hx is false. That's a conditional with a true antecedent and a false consequent. So when x refers to 0, this conditional is false, because it has a true antecedent and false consequent. So this conditional is not true of everything in the universe, and therefore this universal is false. And so we can say that it's false. Okay, let's look at for all x if fx and gx. So for all x, so what I'd like you to do now actually is pause the video and write down, circle what you think the answers are for the rest of, well, actually let's do the next two sentences, and then I'll have a comment on the last one, because the last one's hard in a certain way that I want to talk about. So do the next two. So pause it, do for all x if fx and gx, and some x, gx, and hx, and then restart the video and see what I have to say. Okay, so for all x of fx and gx, well, when we assign 0 to x, then fx is true because f is true of 0, and gx is false because g is false of 0. So when x refers to 0, true antecedent, false consequent. So when x refers to 0, false conditional. And so the conditional is not true of all the values in the domain. And so again, this universal generalization is also false. Okay, let's look at some x, gx, and hx. So it's an existential quantification. So it says for at least one value in the domain, when you assign that value to x, that's true. Okay, so if we assign 0 so that to x, then gx is, well, g is true of 1, but it's false of 0, so gx is false. We don't even need to worry about hx. We now know that the conjunction is false when x refers to 0, because it has its left conjunct is false. What about when x refers to 1? Well, g is true of 1, and h is true of 1, so when x refers to 1, gx is true, and when x refers to 1, hx is true. So when x refers to 1, this is true and that's true, and so the conjunction is true. So there is a value in the universe such that when x refers to it, that's true, and so the existential is true. It's true. Okay, now this one is hard. This one's much harder to read. Why? It's because of all the negations. They make it much more complicated to understand. So one way to think about dealing with negations is to try to move them in as much as possible using our different negation equivalence theorems. And you have to use equivalence theorems for what I'm about to do. So if we think, well, Qn is an equivalence theorem. It says you can move a negation across a quantifier, and whenever you do, the negation changes signs. So what we really have is, if we use Qn, we have this, right? Oh, I forgot the x. Good. So Qn from that would give us this, and vice versa, so we go back and forth. And now, De Morgan's is also a biconditional rule, which lets us go back and forth. So it says if you have a negation outside of if you have a negated conjunction, that's equivalent to the disjunction of negations. And so this is actually equivalent to that, right? That's De Morgan's. And note that, again, we can go back and forth. So what we're doing is we're taking the initial sentence and we're transforming it into something that's easier to understand. And once it becomes something that's easier to understand, then it's easier to know is it true or false. But in doing that transformation, it has to be an equivalence transformation so that what we start with and what we end with have the same truth value. So that if we conclude that what we start with is true, what we end up is true, we know that what we started with is true. And if what we end with is false, then we know what we started with is false. So we can transform sentences, but they always have to be equivalence transformations. And one more transformation we can make is double negation elimination. And so now we have, for all x, gx or hx. So this is less logically complicated than this is, right? If you look at the tree for this is a lot shorter than the tree for this, and that means it's less logically complicated and therefore easier to understand. So these two things are equivalent, but this one's easier to understand. So let's look if it's true. So for all x, either gx or hx. Well, if we assign 0 to x, well, g is false of 0 and h is false of 0. So when we assign x to 0, that's false and that's false, so the whole disjunction is false. So it's not the case that when we assign x to, is it the case that when we assign each object to x, this comes out true? No, there's at least one object for which it comes out false. So this is false, since this and this are equivalent. This is false, and so that is our answer. So one thing you want to do when you're working with sentences and trying to determine whether or not they're true is, if you can, apply theorems that go in both directions in a way that will make the sentence easier to understand. And in particular, move negations in when you can, because that will make it easier to understand, as we did here, right? So we moved the negation in from here to there with Qn, and then we moved the negation from here to there with De Morgan's, and then we were also able to do double negation elimination, and all of those rules, right? Double negation, De Morgan's, and Qn are biconditional rules. They let you go in both directions. Okay, let's look at a second model. So here we have a universe composed of three things, 0, 1, and 2. F, the extension of f is empty, so f is not true of anything. Nothing is a frog. G is true of 0, 1, and 2, and so there 1 is green and 2 is green. And H is true of 0 and 1, so 0 is happy and 1 is happy. But 0 is not green and 2 is not happy. Okay. So remember, these are the things, and these are the things are 0, 1, and 2, and then what we have a list of what F is true of, what G is true of, and what H is true of. So let's look. What I'd like you to do, again, is pause the video, and do for all four of these now. Try to figure out what their truth value is, and then restart the video once you've done that. So welcome back. So, for all x, if it's a frog, then it's green. Well, we know that f is true of, f is false of each object. So for each object, the antecedent is false. If x is 0, the antecedent is false. If x is 1, the antecedent is false. If x is 2, the antecedent is false. So for each object, the antecedent is false. And a conditional with a false antecedent is true. So for each object, the whole conditional is true, and so this is true. Each object antecedent is false. Each object conditional is true. So the universal is true. Let's look at gx and hx. Okay, so well, what about, so what we need to do is we need to take if gx and hx and ask, is it true of 0, is it true of 1, is it true of 2? If the answer to all three of those is yes, then the universal is true. If gx and hx is false of at least one of those things, then the universal is false. Okay, so we have if gx and hx. So let's start with 0. When we assign 0 to x, then gx, well, when we assign 0 to x, then, well, we know that g is false of 0 because 0 is not in the extension of g. 1 and 2 are, but 0 is not. So we assign 0 to x, gx comes out false, and so the conditional comes out true. Let's now consider 1. Well, g is true of 1, and h is true of 1. So this is a conditional with a true antecedent and a true consequent when x refers to 1, and so it's a true conditional. So far, so good. Now let's assign 2 to x. Okay, well, so we know that g is true of 2, but h is false of 2. So when we assign 2 to x, this is true because 2 is in the extension of g, but this is false because 2 is not in the extension of h. So we have a conditional with a true antecedent and a false consequent, so we have a false conditional. So is this conditional true of all the objects in the domain? No, it's not. It's false of one of them, namely 2, and so the universal is false. Some x, gx, and hx. So this says there's at least one thing when you assign it to x, then gx and hx is true. At least one thing is like this. At least one thing is both g and h. Okay. Well, 0 is neither g nor h, because no, that's not true. 0 is not g, because g is false of 0. So when we assign 0 to x, when x refers to 0, this is false. Ooh, let's pause this. So, sorry about that. When we assign 0 to x, then this is false, and so the conjunction is false. When we assign 2 to x, then this is false because 2 is not in the extension of h, and so the conjunction is false. But when we assign 1 to x, then both gx and hx come out true. And so there is a value for which there's an object in the domain. When we assign it to x, the conjunction is true, and so the existential is also true. Let's look at this last one. Something is not f and h. So there's a thing that makes this conjunction true. Something is like this. So something is happy, and something is not a frog. Well, okay. Well, 0 makes this true because 0 is not an extension of f. So this, when x refers to 0, is false, and that means that, when x refers to 0, is true. 0 is also in the extension of h, so when x refers to 0, this is true. So when x refers to 0, both of the conjuncts are true, and so the conjunction is true. So there is a value, a thing in the domain, that when we assign it to x, the conjunction comes out true. So there is a thing like this. There is a happy non-frog, and so this is true. Okay, let's look at the second side. So in the first two exercises, we were given a model and some sentences and then asked, are these sentences true in these models? Here's a different exercise. We're going to be given a sentence and have to come up with a model that makes the sentence true. And we want to produce a minimal model that's going to make the sentence true. So we need, here our sentence is sum x fx, so we need to specify a universe and an extension of f. And so what I'd like us to do is to start with, we're using the numbers, and so the first thing we put in the universe is always 0. If we want 2 things in the universe, 1. If we want 3 things in the universe, we have 0, 1, and 2. If we want 4 things in the universe, we'll have 0, 1, 2, and 3, and so on. So I'd like you to pause the video and write down a model that will make this true. So in this case, the model is simple. We can just we'll put 0 will be our one thing in the universe, and the one thing in the extension of f will be 0. So the one thing that exists will have the property of f, and so there is a thing that is f, and so this is true. No problem. All right, let's look at the next one. So here we have two sentences, sum x fx and for all x if fx, then gx, and we need to make them both true. So again, we want a minimal model, one that sort of modifies this minimally to make one that makes these two true. So again, So this time, though, you need to specify a universe and an extension for f and an extension for g. So pause the video, fill that out, see what you think. Okay, so in this case, it's pretty easy. Our universe will consist just of 1, and the extension of f will consist just of 1. So there's a thing in the universe that f is true of. And then the second premise, all fx and gx, well, right now there's only one thing. So what that says is that when you assign 0 to x, then fx, then gx comes out true. Well, fx is true when x refers to 0 because f is in the extension of f. So for the conditional to be true, we need that 0 is in the extension of g, so that the consequent of the conditional is true. And if 0 is in the extension of g, then the conditional is true. And since 0 is the only thing in the domain, or in the universe, then the universal is true as well. So this works for our these two sentences. And now we'll look at the last set of sentences. So we have some x fx for all x of fx and gx, and some x not gx. So let's copy down the model that we had before and see what happens. Okay. So if we have in our universe just 0, so one thing, namely 0, and we have f being true of f is true of 0, and g also is true of 0, then some x fx is true, and for all x of fx and gx is true. But what about some x not gx? In this case, some x not gx is false, because some x not gx says there's a thing that makes not gx true. So there's a thing. Well, what is it? What does that thing need to be like? It needs to make g false. But since the only thing we have in the universe is 0, and 0 is in the extension of f, then the only thing in the universe makes g true. And we need to have something in the universe that makes g false. So what we'll do is we'll just add 1. Okay, now, but we'll leave 1 out of the extension of g. So some x fx is still true. Now we changed the model. Now we've added 1. So we need to make sure that the original sentences are still true and that the last sentence, some x not gx, has become true. Okay, so some x fx, is that true? Yes, because there's still a thing that's f, namely 0. Some x not gx is now true because there's a thing that's not g, that's not green. Although actually with this text it is green, but whatever. It's not in the extension of g, and that's the number 1. So some x fx is true, some x not gx is false. What about for all x of fx, then gx? Well, now we have to check two values for x. We have to check when the value of x is 0, and then we have to check when the value of x is 1. So when the value of x is 0, then both fx and gx are true because 0 is in the extension of both f and g. And so the conditional has a true antecedent and a true consequent, and that means the conditional is true. What about when x is 1? Well, when x's value is 1, then fx is false because 1 is not in the extension of f. And gx's value is false because 1 is not in the extension of g. So we have when x's value is 1, then the conditional is, well, the conditional has a false antecedent and a false consequent. And a conditional with a false antecedent and a false consequent is true, right? The conditional is false only if the antecedent is true and the consequent is false. So when x's value is 0, the conditional is true. When x's value is 1, the conditional is true. There are no other values, so for all values in the domain or in the universe, the conditional is true, and so indeed the universal is true as well, and this model works. So those are the exercises. So you have there's another document on this page that's the model's homework, and it has some problems like this. And so I'd like you to, for as part of your homework for Thursday, you need to do that handout, and you can either print it out and do it by hand and then scan it back in, or you can, like in a PDF or something, edit it. Or if you there's some other way you think, okay, this will obviously give me the answers, that's fine too. But you need to, one way or another, submit the answers to the questions online. So if you have questions about that, please let me know. Good luck.